Okay, well, welcome back, everyone. So I want to start by thanking Ronan and Teddy for inviting me to this workshop. It's been really fun. I'm really glad I came all the way from Switzerland because just from the interactions we had, um, I'm already going back with a lot of ideas and maybe more workshops that we can attend together to keep working on AI for climate science. So today I'm going to present results from two different projects which use physically informed machine learning. So that's more, let me see if I can move the pointer to the screen. So physically informed machine learning, and that's more the team to the left here of the screen. And then causally informed machine learning, and that's more the team to the right. And I want to really note the contribution of Fernando Iglesias. A lot of the later work I'm going to show in the second part of this talk was led by him. He's at the DLR in Veronica Ering's group. And so the idea is we're going to test these methods to help machine learning algorithms using either physical knowledge on the one hand or causal inference on the other hand. And we're going to do it in the context of machine learning for climate modeling, and more specifically, in the context of emulating what we call subgrid scale thermodynamic tendencies. And don't worry, I'll try to do my best to explain what that means. And in climate models, these tendencies are dominated by the effects of clouds and convection. So just as a quick reminder, atmospheric convection can be broadly defined as any atmospheric motion driven by air density differences. So this is a movie from a storm chaser whose videos I really, really love. So it's from the North American monsoon. And what I think is really visible in this movie is that you can see through how dust is transported, how rapidly these storms that are not that wide in scale can transport tracers in the vertical. So in this movie, you can see it with dust, but for climate models, it matters for temperature, for water vapor, and other tracers. And the problem is that you can imagine this is just a couple kilometers in scale. And so that means that despite the importance for the vertical transport of heat and water, our current Earth system models, the one that we use for long-term climate projections and for which we have to make computational compromises because we have to run them several times for hundreds of years, don't resolve cloud and convective processes properly. So you may dream of having clouds in the climate model look just like the ones you see from the window of a plane, but because of computational compromises with the grid we work with, clouds in our climate models look a lot more like that. So going from this vertical transport movie you just saw to this grid, you can imagine how the current grids we use in Earth system models deform that interaction between fine-scale turbulence and storms and the large-scale climate. And that's why, for a given emission scenario, cloud processes remain the largest source of uncertainty in our current climate projections, or long-term climate projections. And so the idea, so where does machine learning come in? I'm going to jump right to the heart of the topic. The idea is that while we may not be able to run Earth system model at a very fine resolution for hundreds of years, we can run them at a fine resolution for just, maybe a year. That gives us a ton of data. And with that data, we can train machine learning model to emulate the effect of fine-scale turbulence in clouds on the large-scale climate. And so the setup I'm going to use mostly in this talk is a superparameterized setup. So it's a bit of a weird setup, and I want to mention that we also work on a very high-resolution global storm resolving setup, and I'll also show results, but this setup is a little weird, but it has some advantages. You can think of it, a superparameterized climate model, as some kind of intermediate between a high-resolution climate model run on the entire globe and the coarse Earth system model we currently use for climate projections. What you do is you combine two types of models. So you have what we call an exterior model. Here it's on the left. It has a relatively coarse grid. So that's representative of what we run today. So think, 80 or 100 kilometers. It's run at the time resolution of 30 minutes. But then the difference is that in each grid cell, we embed a high resolution but two-dimensional storm resolving model. So those are integrated with time steps of a couple seconds, and it uses a horizontal resolution of 2 kilometers and a finer, no, in that case, it doesn't use a finer vertical resolution. And so the advantage of having that interior model embedded is that then you can explicitly resolve the effect of deep convective systems like the ones from the movie you saw earlier on the climate model. But it's also really an advantage from a machine learning perspective, because since we have such a clean separation between the exterior model on the left and the interior model on the right, we can just emulate the effect of the interior model on the exterior model. So that simplifies the problem of machine learning parameterization quite a bit. And if you train a neural network to mimic the interior model and then plug it back in, couple it back with the Earth system model, you can accelerate it by up to 20 times. Without having a lot of the issues that come with running at a much coarser resolution. And so if you imagine what that model is like, so its role is to mimic the effect of convection on the large-scale climate. Here we're going to make an approximation that the mapping can be approximated as local in the horizontal. So we're just going to, from the large-scale climate condition in one atmospheric column, we want to understand the effect of storms on, and fine-scale turbulence on that same column. So what we're trying to predict from the neural network are going to be radiative fluxes at the top and at the surface and the top of the atmosphere, and very importantly, subgrid heating and subgrid moistening. So this is the evolution of temperature and water vapor that is due to these fine-scale storms. And for that, we need the properties of the large-scale climate at that given column. And so we're going to use quantities that you're probably familiar with: solar insolation, the full vertical profile of temperature, surface fluxes, and specific humidity, which is the mass concentration of water vapor. And so without further ado, I'm going to show you how it looks like offline in an Earth-like context. And so that's work we did to emulate the superparameterized community atmospheric model version 5. And the truth, so what you're trying to emulate is at the top. So that's on the left, it's subgrid water vapor tendency that's 600 hectopascal, so right below the mid-troposphere. And then on the right, subgrid heating, so how much temperature is transported in the vertical. You want to emulate what's at the top, you get what's at the bottom. By eye, it looks quite good. If you use a standard machine learning scores, performance metrics, it looks quite good as well. You just lose a little bit of variability. So to first order, it looks good. But now there's a bunch of issues when you start digging deeper, and this have been bottlenecks that have been preventing the rapid adoption of machine learning parameterization in the climate modeling community. And I'm going to focus mostly on interpretability and generalizability. And so to give you an example related to generalizability, for climate modeling, it's really important to think of the effects of climate change because you're trying to project the climate going forward. And so experiments we like to run is, okay, this is the kind of typical task the neural network is asked to do. You give it a vertical profile and you say, okay, here I pulled one from the tropics. You say, okay, try to predict from the large scale climate property how water vapor and temperature are redistributed in the vertical by storm. So black lines are what I'm trying to get. That's what the neural network does in the reference climate. Here, I'm only interested in neural networks that do, or any machine learning algorithm, it's quite general, that does okay in the reference climate. I don't want to build a straw man, so we're starting from machine learning that do well in the climate that we're trained in. And now you can play these games, which as a physicist, I love to play, which is, okay, now I'm going to warm the surface by 8 Kelvin. That's climate change we hope we won't witness in our lifetime. Supposedly, we won't see that, so at least not globally. And so I play the same game, but now I ask the neural network to predict these profiles in a much warmer climate. And then they fail really miserably. And that's what's nice is they fell by a factor of 5 to 10. So you're not looking at an epsilon here. So neural networks in that case generalize really badly in the tropics of a warm climate they were not trained on, because it's much, much warmer. And I'm going to... So in that case, it's nice because I can just rerun. So that's, it's what we would call a pseudo reality experiment. I can rerun the same super parameterized model, 8 Kelvin warmer, that gives me a truth. And then I artificially only train the neural network on the cold climate, and I see how it does in the warm climate. And so machine learning algorithm clearly failed to generalize in that case. I'll delve into detail as to why. It's linked to the fact that we are predicting thermodynamic quantity. And then as a result, and also a problem linked to that, is that machine learning parameterization are hard to interpret and trust. And we've been working a lot on interpretable AI. But in that case, I won't go too much into detail. I'm just going to say that, if they have such big failure modes, there's no reason a priori why you should trust them blindly. And as an example, I'll show this movie of a neural network that was good, but not that good. And then we coupled it back to the Earth system model and produced a very dramatic crash. And in that case, the crash was resolved. So that was really nice. So right before the whole model crashes, you can see here, the atmosphere is becoming extremely cold, and you have a bunch of gravity waves very dramatically coming away from the failure point, and then the whole model crashes. And there's a paper where we dig into the details of why it made the model unstable, etc. And the question I'm going to ask today is, how can we design data-driven models of convection? So the frameworks I'm going to develop are not specific to neural networks. They can be applied to any machine learning or algorithms. And here, well, I have a pretty machine learning audience. So I don't know if it's worth defining, but machine learning here is defined in the very broad sense. Any algorithm that learns to perform a task from data without being specifically designed for that task. Neural network you can think of as powerful nonlinear machine learning algorithms, which for a purpose fit the training data very well. So how can we make them more interpretable and generalize better? And in this talk, I'm going to show two different ways of doing this. On the one hand, focused on generalizability with physical knowledge, and on the other hand, mostly focused on interpretability, but also I'll show that in some cases it can also help for generalizability using causal inference and more specifically causal discovery tools. So let's start with physically informed machine learning. And in that case, the way we managed to solve the generalization problem I showed you earlier is with a very simple trick, which is simply rescaling inputs to convert what's a very hard extrapolation problem to a problem that's as close to an interpolation as possible, which then machine learning algorithms can do very well at. And it could be called in the machine learning jargon what you would think of as a feature transformation or feature engineering, but informed by physics. And so as you saw, the idea was to break the model as much as we could to uncover its weaknesses. That's really something that some people are a bit afraid of doing because they're afraid of seeing that the model doesn't work so well in adversarial or slightly different conditions, but it's always worth it. Like when you do it, you can learn so much about your model, its weaknesses, and how to fix them that I like it. And then you working with error of 100, 200%, that's much nicer to fix than trying to go for the 1.5%. For these kind of frameworks, at least. And so a generalization experiment was a uniform 8 Kelvin warming. I'll go through it quite quickly. So we train and validate the model on cold simulation. So here it's written aquaplanet, but we've also tried it in an Earth-like context, and we've tried it not only in a super parameterized, but also in a storm resolving context. And so because we mostly focusing on the atmosphere, here, surface temperatures in the case of the aquaplanet are prescribed to a realistic surface temperature profile, and in the real geography case, we run it interactively, but just with the land model. I mean, I'm not going to go into too much detail because that would take the whole talk. But let's first focus on the aquaplanet case, where in that case, it's very visual. So I think that's easier to imagine when there's no interaction with the land and the ocean. In an aquaplanet case, we're focusing on here parameterizing the atmosphere. So we're going to impose a surface temperature profile as a function of latitude that has a realistic gradient from the poles to the equator. That's the cold simulation, and then the warm simulation looks like this. So in the aquaplanet case, it's very clean because you can see that if we train on the cold climate and then we test on the warm climate, there's going to be an entire range of latitude in which the neural network or any machine learning model is going to be subjected to surface temperature conditions it has never witnessed during training. So here we have a very clear out of distribution generalization experiment. And we saw that it failed. And it failed also, and that's some other work we did. So we engineered some neural networks so that they would conserve mass and energy on the column level. And what we find is that even these neural networks that conserve mass and energy have large generalization error. So it's a bit different. We just warmed it by 4 Kelvin. But what that means is that in that case, it's not linked to column mass and energy conservation. It's linked to another problem. And the problem we identified was out of distribution input, which machine learning algorithms, especially when they start being more complex, react pretty poorly to, except if you play a few transfer learning tricks we can discuss after the talk. And so in that case, it's helpful to see the mapping we emulating in its mathematical form, where you're trying to go from large scale, the large scale climate to subgrid scale tendencies. And what we saw is that if we brute force it, this mapping is not what we would call climate invariant. So that function is not the same in the cold climate and the warm climate, and that's the reason why you get the generalization error. So then the idea in that case is that we are in a thermodynamic situation where we know enough about the laws of thermodynamics to rescale the inputs, and in theory you could also rescale the outputs and the general coordinates to transform the mapping so that it's much closer to being climate invariant, so that that function that you learn in the cold climate can also learn in the warm climate. So that's the mathematical idea. And how do we do it in practice? How do we choose the physical rescaling? In some cases, there's a little bit of trial and error. In some cases, we have very robust theory. So the case for the input that's most problematic in our case, where it's a lot of moist convection, we know that specific humidity, so the mass concentration of water vapor in a given kilogram of dry air has a distribution that changes a lot with warming. So here I'm showing you the logarithm of a histogram in the training set, so the cold climate, and then the generalization test set. So I want to say that we also used the validation set in the cold climate. So we really designed the neural network so that it did well in the cold climate. But if you look at this distribution of inputs, clearly the water vapor concentration in the warm climate reaches value it has never seen. So you go up to value of 30 grams per kilogram that you do not have in the cold climate. And with this big tail that goes way above this one, you know that the support of the distributions are going to be different enough that you're going to be confronted with extrapolation. But now we know how the upper bound of specific humidity for a given temperature and pressure varies as we change temperature and pressure, because we know the cause is Clapeyron equation. And so we know that as you warm air, the amount of water vapor it can hold before water vapor condenses into clouds increases near exponentially. So then we can use this equation to rescale specific humidity into relative humidity. So that scaling doesn't involve any fitting. This is from physics. We exactly know the constants. So we can form relative humidity. And if you look at the logarithms of a histogram, the distributions don't exactly align, but that's not what matters too much. What matters too much is that the support now is very similar, and you get a lot of samples that have similar values. And just by rescaling this input, which can be done in many different ways, you can do it as a custom layer, you can do it as a custom data generator. If you already know which rescaling you're going for, you may as well just duplicate your data set. We already gain a lot in terms of generalizability, and that's for a particular profile, but it also works in terms of average statistics. So if I look at the vertical profile of the mean squared error in the subgrid scale moistening, we already decrease the error by a lot. And then, and I'm going to go quite quickly. We can go back to it at the end. If some of you are interested, you can play these games with other inputs. For specific communities, it was quite obvious what to do. For the other one, that required a little more trial and error. So because a lot of the problem is tropical, what we found is that we could use a measure of coarse scale buoyancy. Normally, you need fine scale data to access the exact buoyancy of air, especially in the context of convection. But you can make a few assumptions and you can derive the buoyancy of the more static energy conserving plume. And that basically you're going from a thermodynamic quantity to something that's more dynamic, so that's less likely to vary with climate. So we used one that was developed by the lab of David Neeling, Kathleen Shearer, etc. They developed it in the context of observations of mesoscale convective systems over the Amazon. So that's the general definition of buoyancy, and then you can derive a coarse scale buoyancy by conserving a certain quantity. Details are in the preprint, but if you look at it from a distributional perspective, you go from what's clearly an extrapolation because temperature increases quasi-linearly, air temperature increases quasi-linearly as you warm the surface, to something that's much closer to an interpolation. And then you can repeat this game with all other inputs. So you can rescale the latent heat flux using the bulk surface aerodynamic formula, etc., until you get to a mean performance that's almost as good as neural networks that were trained directly in the warm climate. And at that point, we were happy and we would say, okay, we demonstrated that that idea worked. It works in an aquaplanet setting. I'm going to show that it also works in a real geography setting. For instance, using maps of near-surface subgrid heating. Here I'm showing the coefficient of determination, not to be confused with the coefficient of correlation. So that's a very standard regression performance metric we use in machine learning. 1 is perfect prediction, 0 means the error is as large as 1 standard deviation. And then it can go down all the way down to minus infinity if your model is really, really terrible. And so you can see that before the rescaling, we have this really big generalization problem in the tropic that is not perfectly solved, but mostly solved by the physical rescalings. And it works even better for more atmospheric centric quantity like subgrid heating. Okay, so I'm almost at the end of the first half of my talk, but the takeaway here is that in that case, we have enough physical knowledge of the system that we can design a feature transformation. That means that any machine learning algorithm I'm going to train on this mapping is going to have better generalization property. And the advantage of that, I know there's a lot of machine learning people in the audience, is that this kind of feature transformation can be combined with any kind of transfer learning trick you can think of, because it doesn't act exactly on the same things. So you can still use tricks from domain adaptation, etc., in conjunction with this rescaling. So in that case, it's kind of something you should absolutely mindlessly do if you have physical knowledge about the system. Now, what's fun, and that's another thing we do research on, but in that case, you can already learn something about the underlying physical system by looking at why exactly. So why exactly does it generalize so much better? It's not trivial to investigate, but we went in, and I like to show these, to look at these convective parameterization in terms of matrices, where you get the input at every vertical level, and then you get the output at every vertical level, and you can see how perturbations at different levels of the atmosphere lead to different responses. In that case, it's not trivial because we wanted to have a sense of the nonlinearity. So I based this analysis of SHAB value. So that's X-AI tool that gives you how the contribution of different inputs change the outputs. You can go to the paper for details on how we derive these matrices, but basically it gives you the response of the output as the nonlinear response of the outputs as a function of the inputs at different level. And without going into too much details, here what you can see is that we went from a big blur of red and blue to something that's much closer to the diagonal. And so what that means is we went from a mapping that's very non-local in the vertical. So we had temperature high up or at the bottom that would determine how subgrid moistening or heating changed at different vertical levels, to something that's much more local. because the buoyancy already takes care of a lot of how the boundary layer talks to the free troposphere. And then the relative humidity is a much better input to know when you condense, when the water vapor is going to condense, because as soon as you hit 100%, water vapor is gonna condensate into clouds. And so you go from something non-local to local, and we hypothesize that's why the climate invariant generalizes better. And we used XAI tools in other studies, and now that's in a global storm resolving context to analyze also what caused the big crash I showed you earlier. And in that case, what you can see is that the diagonal is kind of erased, and you have a lot of these bright colors higher up. So what that means is you have upper atmospheric variables, at least a neural network learned that upper atmospheric variables influence convection below it. And this is contrary to what we know from physics. We know that convection is mostly bottom up. So here, the neural network learned a shortcut. It learned that there was some kind of correlation between the upper atmosphere and convection inside the atmosphere, and it used that. And the problem is that is what's leading to the instability, because you get a reinforcement of tiny little perturbation in the upper atmosphere. And so in that particular case, and that was done by co-authors, so that's done by Noah Abranovich, Chris Bretheton, they showed that if you cut the upper atmospheric inputs, you stabilized the climate simulation. But now that probably sounded very technical, because it is, and it sounded a bit post hoc, right? We had a problem, it learned a bunch of spurious relationships, then we go after the fact and we change a few things and then we stabilized it. But it kind of asks the question, okay, if we don't have a priori physical knowledge of the system, because initially I showed you a very nice case in thermodynamics where we have a lot of knowledge, but there's a lot of cases in machine learning where you don't have such knowledge. Is there a way to a priori learn to avoid spurious correlation? And that's a lot of the idea behind the growing field of causal machine learning, where you try to combine the results from causal inference with machine learning predictions. And we've explored it, and there's a lot to explore, but we've explored the surface of it to select the inputs of our machine learning models. And so in that case, and in the first paper where we did it for climate application, we called it causally-informed machine learning. But really what we're doing here is causal feature selection. So we're really using it to select the inputs. So in the previous case, could we have learned a priori to not select the upper atmospheric inputs that led to spurious relationships? And for that, what you can do is you can phrase your regression problem as a causal discovery problem, so that you can select the inputs a priori. So before you even train any machine learning algorithms on your problem. And the hope is to do that without degrading performance. And so for that, we rely, because we can't act on a system, or at least we put ourselves in a situation where we could also learn from observation. So in that case, you can't really act on the Earth system, or at least you probably shouldn't, to order one. So we rely a lot on algorithms that learn causal relationship, but I should say they approximate causal relationship from time series. And so we learn with algorithms from the TigerMath library developed by Jakob Runger and co-authors, and these are improved version of algorithms that we use in economics. And what they can do is they can take a multivariate time series, and from these time series, they can approximate causal links. So they can approximate parts of the causal graph or the entire causal graph. But really what they're really good at doing, because without acting on the system, you can never really say what's a true causal driver. But what you can say is you can identify what's a co-founder, so you can eliminate spurious correlation, even if you can never say I truly discovered a causal link. So this tells us which links are spurious. And then the idea is pretty simple. You identify spurious links, and then you say, okay, these inputs I'm not going to learn. I'm not going to connect them to the outputs, so that whatever I train then doesn't have these spurious correlations in it. So it relies on a couple of assumptions, especially the PC1 algorithm we're going to use. So it relies first on two conditions, which allow you to define the causal graph So I think very theoretically, they say that the causal graph should correspond to the d-separations in the data, but a more plain way of putting this is that whenever y depends on x, they should be connected in the causal graph. And whenever two variables are independent, they should not be connected in the causal graph. So that just allows you to define your causal graph. And then there's another assumption called causal sufficiency, which is very hard to verify in practice, which says that all common causes are observed. So we say that in our data set, we have enough observed variables to be able to eliminate confounders. Now, in practice, you can't really get there in our system science, so we say it's approximately verified. It's verified enough that we can relatively to other eliminate some variables for being spurious. But of course, if you observed every single thing in the system, it would be we could get much closer to the true causal graph from the time series. And then the last assumption that you need to run this algorithm is the assumption of causal stationarity, which can be relaxed in some cases, but here basically we're going to say that throughout the time series we use, the causal graph doesn't change. So the causal graph itself is stationary. And then you can run these algorithms and it allows you to eliminate a lot of inputs. So that's the graphical relationship where you start from the prior that all inputs are connected to all outputs. Then you run your causal discovery algorithm and you end up with something that's significantly sparser. So going back to the matrix representation, for the exact same mapping I showed you earlier, except that I'm going to add the full vertical profile of the wind as an input, because in that case, that's what Fernando did. And what you get, and I've played a lot with it, and it took us a few iterations to get there. So at the time, it was a bit more empirical, is that we said, okay, I have my full Earth system model. I'm going to pick one location. At this location, I have my time series. I'm running it through my causal algorithm, and then it's going to tell me 0, you're not connected, 1, you're connected. And so you get this little matrices of zeros and one. And so here again, I'm putting the outputs on the y-axis and the inputs on the x-axis. So you can see that it's quite intuitive, right? Like water vapor is connected to how storm redistribute water vapor at the exact same level. So we're happy physically, we're not getting something that's completely absurd. And then you can get that for one sample. And what we want to know is whether this is worth it compared to the simple baselines of only using correlation to select our input. So here, if I do very, very naive correlation, so this is Pearson correlation coefficient, so double signs. I could just use the correlation matrix and put a threshold on it and only keep the most correlated links between inputs and outputs. But you can see that if we do that, we retain spurious links. So these upper atmospheric links I told you about, here you can see that upper atmospheric in our case, well, you don't really, sorry, there's no pressure here, but imagine the tropopause is here. So the tropopause is roughly 10 kilometers above your head at your latitude. So here we have stratospheric water vapor, and you can see that here it learns that there's influence of stratospheric water vapor, strong influence on the moistening below. So that's what we didn't want to have. So there's a spurious correlation. So if we just use correlation, the neural network is going to want to learn that correlation, which isn't physical. Whereas if we take the 1 and 0s I showed you at one location, and then we make the assumption of, I guess, a spatially uniform causal graph. So we repeat this 1 and 0 matrix for every single location on the Earth. Then this is the proportion of locations where you get the causal links. And then you can threshold that and say, okay, this is the causal links that I want to keep. And now you can see that it's much more physical. It got rid of the spurious links. It knows to retain links, the effect of surface fluxes and insulation on how storms redistribute water vapor, which is what we want. And now we're done with the causal discovery part for that case. And so now we want to go to the next step, to the causal machine learning part. So then we're going to compare two different types of models. Yes.
So before you go, can you explain how does this causal discovery thing work?
Yeah. So here in this example, we only really use PC1.
What is the principle? How do you
So it's
how do you discard it based on what?
so you start with the prior that everything, and I'm sure I'm not going to do the best job at explaining it, and in our papers it's explained more rigorously, but let's see, I'll try to give you a high level overview. You start by assuming that everything is connected, and then we use this terminology that we have the parents and the children. So the parents are the causes and the children are the consequences. So you take a given child and you're going to assume that everyone is their parent. So everyone is connected. And then you're going to conduct independence tests. And so then you can choose how you conduct these independence tests. But in the simplest case, you're just going to use partial correlations. And then you're going to remove based on this conditional independence test, you're going to remove all the inputs that don't help you predict the outputs at a given statistical significance level. That's also a hyperparameter of your model. And then you're going to do it iteratively, because then you say, okay, I start with all the parents, then I'm going to take the strongest parent, and then I'm going to condition my test on that strongest parent. So now I'm going to do a simple regression on that parent, and I'm going to use the residual to do the conditional independence test. And then I'm going to eliminate more parents. Then I take the two strongest, I'm going to eliminate it, and then it's iterative. And then you're left with a set of parents for a given child. So that's the PC1 algorithm. And then the PCMCI algorithm adds another test called the momentarily conditional independence test. And then that will run further tests to eliminate it, like parents that are strongly, like it's going to control for the strong autocorrelation in time that you have, because all of these are based on lagged. So, you know, when I say, is it conditionally independent given a prediction task, I'm doing lagged multiple linear regression over and over again. And so it's going to take into account the fact that because of autocorrelation in time, some parents are thrown in where really you're independent from them. So it's you know, you start from a null hypothesis, then you identify first parents and you say, is this new parent helpful given that first parent? And if it's not, then there's a co-founder, right? That parent causes that parent you want to eliminate and the child. Does that answer the question?
Yeah.
Okay, cool. And if you go in the paper, it's much better explained because it's actually Jakob and his postdoc who wrote it very rigorously with the right set notations and everything, which I could try to mimic on the board, but maybe we can keep it for a fun exercise at the end. Okay, so now what we want to compare is non-causal neural networks and causal neural networks. So non-causal neural networks, we're going to change our baseline a little bit. Since for every child, we want to identify a set of parents, now our neural networks are only going to predict one output at a time. So that way, the non-causal neural networks keep all inputs, whereas the causal neural networks, they first run the causal discovery algorithm, and they only keep the parents that are causally related to the child. And so that's what we will call the non-causal neural network and the causal neural networks. So causal neural networks, in essence, they use these causal discovery algorithm to eliminate the spurious inputs so that you only keep the inputs that are most causally related to the output. And again, maybe my language is a little bit slippery. You can't ever identify the true cause from time series. You can mostly eliminate co-founders given a conditional independence test. And now you can compare them. Now you can train them, you can plug them back to the climate model, and that's work from Fernando. I was a collaborator, but I don't want to take credit for it because that was like a year and a half of really hard work. You can take these causal neural networks, you can plug them back in the Earth system model, And here you have the brute force.
What do you know? Same as before.
Yeah, so I learned the same as before, and not only do I do that, I learned the same as before, and once I'm happy, I plug back, Fernando plugged back the neural network in the climate model. So now I'm looking at online runs. And you can look at statistics and biases. And for example, this is the root mean squared error of global temperature below the tropopause. And if you look at the bias, you can see that the brute force neural network is much better than the causally informed neural network. It leads to lower biases. And most importantly, the model, like almost all of the causal neural networks that were well trained, didn't lead to crashes. So it also, at least empirically, seems to have a stabilizing effect. The SPCAM reference. So that's, we still run the superparametrized model in parallel as a truth. And it has a very low residual error because we compare it to some kind of temporally average state. So we know we can't really go below that. As long as we close, we're happy. Okay, and then you can, okay, so maybe now is the time to take a step back before I show more matrices to interpret the results. Okay, so what did I just show you is that you can run, before you train any kind of machine learning algorithms, you can run these causal discovery algorithms on time series. It's pretty cheap, it's not too bad. Obviously, following best machine learning practices, you should only do it on time series of your training set. And then you can identify inputs a priori that you can then train your machine learning algorithm on so that it doesn't learn the spurious relationship. And you can do that without physical knowledge, which is convenient for some systems where you don't have a lot of physical knowledge. And so now I'm looking at the same CHAP matrices. So I think Nando used the same kind of nonlinear recipe I used in the climate invariant paper. And he subtracted these nonlinear influence matrices. He did standard case minus causal case. So red is where the brute force neural network gives more importance, and blue is where the causal neural network gives more importance. You can see it's kind of reassuring because the causal neural network shifts away the importance from these spurious upper atmospheric links to the diagonal, which is a stabilizing local damping. So in convection, it's really nice if your neural network has some local damping effect, because you don't want water vapor to come and then it says there's even more water vapor that comes from convection. That's completely unstable and that's not physical. In practice, if you add water vapor at a given place, then it's going to get advected away, it's going to get diffused away on a very long time scale, but mostly you should get a negative local response. So we're happy that the causal neural network is able to identify this more local response. Another thing that's fun, and I'm not going to go too much into it, but it's linked to the generalization problem I showed you much earlier, is that if you compare the causal links you find in the cold and the warm planet, they're mostly the same. And that's very reassuring to us because when we think of causality, we think of underlying more general relationships, and we don't want these relationships to change whenever the environment changes. So this seems quite robust. It made us happy. That's a game I played a year and a half ago for a conference. I just wanted to show, hey, these are not methods that are, these methods are acting on different things. So the physically informed is a feature transformation method. The causally informed is a feature selection method. So you can play the game where you put both at the same time. And then I was able to divide the number of inputs by 8 and still generalize well. So I was like, hey, but this is more for fun. I don't know that I recommend combining them together systematically, but I just want to say that as long as you develop these methods to not all act on the exact same aspect of the algorithm, you can combine several methods together to gain not only physical consistency, but possibly interpretability. In that case, causally selecting your feature brings you a lot of sparsity or parsimony, depending on how you see it. So you can decrease the number of inputs, possibly increase your number of trainable parameters if you care about such things. And then in terms of Outlook, I want to show something that we did with my research group at the University of Lausanne. It was led by my postdoc, but that project was really fun because I think everyone in the lab worked together. So it's the postdoc, but also the PhD students, me. It was like a big team effort led by my postdoc. And we also worked with the Runge group. And I think it kind of came from it came from two things. First, a little bit of frustration because that method we had to threshold the causal links seemed a bit ad hoc, where we counted the number of locations. And also a postdoc of Jakob called Andreas Gerhardus, who's like who's a collaborator on the preprint I just put on my website. I'll give you the link to my website at the end. It just got accepted for climate informatics. We said, okay, can we be a little more systematic, where we have a bunch of multivariate time series from a phenomenon that we know is the same? Can we be systematic in how we select input so that we feed this ensemble of multivariate time series, and then we get a single set of causal drivers at the end? And so that's, oops, am I over time?
No, you have a question. Just,
Oh.
so you are five, you still have 5 minutes, plus 5 minutes of question.
Okay. Hello, what is the set of initial inputs you start with, and how do you select those? Can you use this causal discovery algorithm on high-dimensional inputs? So in the previous case, it was the exact same inputs I showed earlier, and I selected them for each output. That was a case where there were already quite a bit of inputs, but here I'm showing you a case where there's going to be, so I'm answering your question now because I'm going to show a case where we have a ton of inputs to choose from, way more that we can possibly keep if we want to not completely overfit the training set. And so if you add an assumption, the assumption of common causal structure. So I'm going to show you an application to tropical cyclones, but with storms, you can also think, we get a lot of realization of the same storm. And we can make the assumption that these storms are ruled by the same underlying causal relationship. So if we make that extra approximation in the conditional independence test, we can sample from different phenomena from the training set indiscriminately, and that allows us to have more confidence in the causal links we find, and to output a single set of causal drivers for a given mapping. And so if we apply this to the statistical prediction of tropical cyclone, so we played games where we're trying to predict surface intensity, so the maximal surface wind speed, minimal sea level pressure, and precipitation. We want to not only identify, so we have a lot of meteorological variables to choose from. We wanted to kind of be agnostic. So we have many different variables at many different vertical levels in the atmosphere, in different horizontal sectors. So we averaged them in the inner core and the outer core of the tropical cyclone, and also at many different timelines. And so that's what we call a feature, a variable at a level in a horizontal sector at a given timeline. And now we ask the causal discovery algorithm, can you pick the ones that are most relevant for us to make the predictions? So we threw in a lot of meteorological variables. I don't have time to go into too much detail, but this is a curve that when we saw it, we were very happy. So we have a training set and a validation set that are quite independent because we separated them by storms. So there's no spatial or temporal autocorrelation because we chose storms that were not on top of each other, which almost never happens for tropical cyclones anyways. So training set 50 tropical cyclones, validation set in that case 50 tropical cyclones. And that's the curve where we're really, really happy. Because in that one, it's very simple. So we're just training multiple linear regression. We also tried it with random forest. And what we have, and that's expected, is so here we vary the hyperparameters of the causal discovery algorithm so as to allow more and more features. And the more features we have, the better we can fit the training set. So that's what we were hoping. And then what made us happy is this validation set behavior, which really shows that the first features selected by the causal algorithm are really the most important that allow you to generalize the best, because they give you a lot of performance very quickly, and then it decays. So it really selected the most relevant features first. And it outperforms, and I don't have time to show that, but other feature selection baselines. So we did random, we did one based on XAI. So we train a random forest with all inputs, use the feature importance to select the features. That's pretty hard to beat. So we beat it a little bit, but I wouldn't say we crush it. But that's pretty state of the art. And then we crush lag correlation. And then we also beat more complex models. So we trained an LSTM well enough that we were happy with the performance, but then it has a hard time generalizing. We really crushed a non-causal baseline of the same simple algorithms. But what's quite remarkable is that the causal feature selection worked well enough that it gave just a linear algorithm, in that particular case, competitive performance compared to an LSTM that was pretty well trained for the prediction of 10-meter wind speed. And finally, you can use the causal links you identified to learn more about physics. And so, for example, we can compare the causal drivers. So that's the proportion of, inner core relative humidity links that are chosen, outer core divergence, etc. And so then you can compare what the causal discovery algorithm selected in terms of feature to the correlation to understand why the lagged correlation was misleading. So for example, in the case of statistical forecasting, so you kind of have to do it case by case. In the case of the statistical forecasting of tropical cyclones, if you just do it based on correlation, it's always going to pick variables that are as close as possible to what you're allowed. So if you say, I'm going to predict 1 day in advance, it's going to say, okay, take all the correlation is going to be take all the variable right now, like an hour ago, 2 hours ago, etc. And it's not able to see the longer term dependencies because it's just focusing on correlation. And also we were happy because from a mass adjustment perspective, it's nicer to see that here, instead of the quick vertical velocity, the causal machine learning was relying on outer core divergence, so more the steering flow and how tropical cyclones respond to large-scale convergence, less large-scale divergence. And we were happier from a physical perspective with the causal discovery as well. And that preprint is on our website. Okay. To conclude, I hope I convinced you that there's a lot of opportunity for any machine learning algorithm to be informed either by physical knowledge, and when there's no physical knowledge, causal discovery algorithms, even just to select the features, which sometimes can be very helpful because we not only need to select variables in Earth science, we also need to select how to reduce their dimensionality. And so they can guide you in which location in which dimensionality reduction methods are most relevant to make predictions that generalize well. And also it helps with interpretability, because if you select the features to only keep the most relevant, you just end up with, 10 very relevant features. Your machine learning algorithm becomes significantly easier to interpret than if it takes 150 inputs, for instance. And both methods can be combined, because in the examples I gave you, and we have other examples where we act on different parts of the machine learning algorithm. The first one is a feature transformation. The second one is a feature selection. So these can be combined together, and they can also be combined with transfer learning methodology and pretty much any regression algorithm you can think about. So with that, I thank you. I think I put everything on arXiv and on our website. Some of this work has been accepted for publication. Some of it is under review. And you can feel free to email me for any questions you have. And then I'm going to keep advertising this, although I think I've done it already quite a bit in this workshop, is that ECMWF, in partnership with the University of Luxembourg, developed this huge open MOOC on machine learning and weather and climate. So I helped with 2 of the classes on physics-guided machine learning and parameterization. And so there's nice little notebooks, for example, that are accessible on my website and on the MOOC. There's these reproducibility challenges these days. So for the climate invariant part, we have a simple Google Colab notebook where you can load part of the data and reproduce the climate invariant neural network example. And then if you also are interested in metrology, or we work a lot on constraint machine learning too, where you constrain the outputs. We also have an example on physically constrained post-processing of surface variables in Switzerland. Yeah, and with that, I want to thank you and happy to take any questions.
You have a question for Tom?
I was curious in your WhatsApp example you showed, why did you didn't take into account the
which then I do in the causally informed part. Yeah, so in the first part, we found that in that particular case, wind was not too important. It's not that it's not important to the system, is that in the context of superparametrization, having the core scale meridional wind doesn't give you a ton more information. And I just wanted to keep the example simple. So the little epsilon of performance I gained from the wind, in that case, I decided that it wasn't worth it. But if you want to optimize the performance, that core scale wind information helps a little bit. That's what we kept it in the second one. So
does it mean that Vinci or this kind of stuff that's not that important with whitening and
So normally it is in the super parameterized setup, and you're getting to a limit of that setup from a modeling perspective. It's not, because the way momentum is transferred is awkward because you're putting two-dimensional cloud resolving models into a climate model. So that's one of the biggest limits of super parametrization, is that you momentum flux exchanges from the large scale to the subgrid are unrealistic. And I would say that's the biggest drawback compared to global storm resolving model. So you touched the weakness of super parametrization. And I'm not going to pretend it's not there, because it's definitely one of the reasons why you still want to learn from global storm resolving model. Otherwise, we could just use super parametrization for everything because it's simpler, it costs a little less, but momentum fluxes is where you get stuck. And these kind of shear influences on convection you don't get right. Yeah.
Yeah, thanks a lot. Great. Regarding the causal discovery algorithm,
Yeah.
so I don't know research, but I understand that it based the feature selection or the prioritization based on some correlation. So
Statistical significance.
Linear relationships between the test, even if it's in some kind of statistical framework. Is that correct understanding? Or
Yeah, so in its default, it's not, you can do other tests that are nonlinear, like Gaussian, etc. But in its default configuration, the PC1 algorithm would use a simple partial correlation test, which corresponds to a linear approximation. Doesn't mean the whole system is linear, it just means that the conditional independence test is linear, but you can change that. That's a huge advantage of causal machine learning over just causal discovery full stop, is that we have a validation set. So a lot of these causal discovery algorithm parameters we treat as hyperparameters. And so you can just check the training and validation performance. And so it gives us a big advantage compared to just causal discovery. And it makes me, I don't know, as a physicist, it makes me happy, because if I just use the causal discovery algorithms out of the box, I have a really, really hard time just believing the outputs because the hyperparameters may not be right, etc. But if you validated it via a cross-validation procedure that you trust, then you know that the causal drivers you learn, I don't want to say causal graph because you're only learning a little part of the causal graph, you gain a lot more confidence. So the linearity of the partial correlation test, the statistical significance threshold is a huge that's how we vary the number of parameters. Those are all hyperparameters in our case.
And maybe a related question is whether that would make sense or not to, instead of solving on one first the feature selection test and then having the learning, trying to address both things at the same time, whether that's investigating the better, or whether it's much better to have to.
Well, it's not really, like, almost no one is doing that, so it's very emerging. So I don't know if there's a systematic way. The causal, I have a hard time seeing what would be the advantages of it, because in our case it's not that expensive to run the causal discovery algorithm. So we get several sets of inputs, and then we can run any regression algorithms.
Okay, you could also use within the causal discovery algorithm the regression algorithm you use at the end for
correct, and then that would lead to different sets of inputs. So yes, there is an underlying assumption here. If you run the causal algorithm out of the box, like PC1, it's going to use its conditional independent sets are going to be based on lagged. It's an autoregressive model, but it's going to be equivalent to a lagged multiple linear regression. And so, in a sense, it's maybe a bit more appropriate to select inputs for multiple linear regression or models that are closer to linear than others. You can relax that, but then it gets really expensive. So
then maybe it's better. I don't know. Maybe it's better to have maybe independent. Maybe you're more robust is not use the same algorithm for regression and for selection.
Yeah,
kind of relationship.
Exactly. In the end, yeah. In the end, I wouldn't make claims that I found a completely causal machine learning algorithm. Really, we use it as a regularization technique, right? So, but the advantage is it can be tested. That's the advantage of causal machine learning. You can have scores, you can have generalizations, and you can test a lot of combinations quickly. But yeah, it's barely scratch. That selecting features is just one thing you can do with causal algorithm. You can do so much more. And I think it's just starting to be done.
Yeah, thanks a lot, Tom. It was very nice.
Okay. This is Pedram. Hi, Pedram.
Hey, can you hear me? Hello?